Electric discharge lighting. What we're going to be looking at in this presentation is the operation of electric discharge lighting, as well as some background information on some of their characteristics. First thing we want to look at is some of the ratings that have to do with electrical lighting applications. First item, light is an electromagnetic form of radiation. We can only really see from the red to the violet spectrum. And once we get into electric discharge lighting, we're going to see that the light that's being produced is actually ultraviolet. So how is it that we can then see it? Because it seems to be outside of the visible light spectrum of the human eye. The other items we have are CCT, or correlated color temperature, which is the relative feel of the light. Is it cool, warm, something like that? And so a lot of different types of electric discharge lighting will be in the cool area as opposed to the warm. And when we get into electric discharge, there is a choice depending on what the coating is and what we have on the tubes. It can be all sorts of different types of coloring. And so it's important that when you're relamping that all of the tubes you replace with are the same CCT rating. Otherwise, you end up with a patchwork array at the very end of the job. Last one is CRI. Incandescent gives the best color rendering index, which means it is the best at replicating all of the colors and for the human eye to distinguish the difference between them. When we get down here into some of the electric discharge types of lighting, you'll notice the CRI is quite low. And so we're going to see that there are some advantages to electric discharge lighting as well as some disadvantages. They're not fantastic at providing distinction of colors for a typical individual. Efficacy. How effective a light is at illuminating. Incandescent, we can see here from this particular chart, and these numbers vary all over the place depending on who you cite them from, but this particular group is saying incandescent would get about 4 lumens of light output per watt of electrical energy in, whereas on the electric discharge category, if I had a high pressure sodium electric discharge lamp, it can put out 140 lumens per watt. And so you can see here, efficacy-wise, it is far more effective at producing lumens of light for electrical energy in. So here are the different types of light sources that we have in the electrical industry: incandescent, electric discharge, and LED. The first one, incandescent, we're going to touch on briefly, which is tungsten and halogen. Incandescent is a standard bulb, often referred to as the Edison bulb, and it is establishing light by making a small tungsten element glow extremely bright with current flow on it. And there is an inert gas inside this little globe that simply protects the tungsten from getting damaged and sort of lowers the oxidization of that tungsten filament. The main step forward in technology for incandescent was the halogen lamp, and that's where we took the same tungsten filament, but this time we enclosed it in a small capsule that was filled with a hydrogen gas, and there's all sorts of different types of gases that we would put in there as well. And really what that did was it increased the light output, but it also ensured that the tungsten element lasted longer. So in a typical bulb, what would happen is that the tungsten would slowly evaporate essentially from that filament, but in a halogen, it would reattach. And so it simply made it last longer. Electric discharge lighting. The light source is now not from a glowing element, rather it is generated through electron excitation as it flows through gas vapor. And the fixtures require something called a ballast. So let's look at how they actually function. There's a few different categories. There's a fluorescent, compact fluorescent, and high intensity discharge categories of electric discharge lighting. Fluorescent lighting. It's a low pressure mercury vapor inside a glass tube. This is a linear, so straight tube. It's got 2 electrodes at both ends, and it's got a tiny little filament, and the filament doesn't glow when it is energized. Rather, it is a point for electrons to conduct to the mercury vapor inside this tube and progress over to the other filament that would be at the other end of the tube. What happens is as the electrons move along the atoms of the mercury vapor, it excites all of these atoms, and that excitation causes UV radiation to be generated, and the UV radiation generated then interacts with the phosphor coating on the inside of the tube, and that is what provides the visible light. I'm sure if you've broken a linear tube before, you know that there is a powder coating on the inside, and the powder coating is really what allows us to get visible light out of this. Of course, one of the main detractions of fluorescent lighting is that when we are relamping a large facility where there's hundreds of lamps being replaced, they need to be disposed of properly, which means you can't just throw them in the garbage bin, because what ends up happening is we release significant quantities of vaporized mercury into the air. So there's a number of different types of devices we can use to capture that gas and to recycle the glass and the metal end caps. Lots of different physical arrangements. We have bipin and we have single pin. Bipin are typically for the standard output, and they have two separate electrode pins at the ends of each end of the tube. And the way that we identify most of the linear tubes is through a T rating. So T means tubular, and then 17, 12, 8, and 5. There's also a T10. The 12, 8, 5, and 17, these numbers indicate the number of eighths of an inch. So 5/8 of an inch diameter, 8/8 of an inch, which would be 1 inch in diameter. T12, which was the most common until probably the mid-90s, is quite a large type of tube, and this is 1.5 inch diameter. Most people are replacing T12s with T8s and T5s, but that typically means that the entire fixture has to be replaced because a T12 consumes more energy than a T8, and a T8 consumes more energy than a T5 for the same output of light in lumens. There's other types which are recessed double contact, and these are high output and very high output. So these are used in places where the linear tube is very long, so a non-standard length, and also in areas where we want to have significant production of light, or in areas where it is cold and we want to have light output in those cold areas, because fluorescent fixtures don't illuminate very well when the temperature around them is very, very cold. So things like walk-in coolers, walk-in freezers in a big warehouse where a forklift drives in, you need a lot of lights in there, and they need to be able to operate in sub-zero temperatures. So this recessed double contact, and these are single pins. Let's take a look at some pictures of real ones. So there's a T5. This is a T8, so a little bit bigger, you can see diameter. This is a T12, a little bit larger diameter. All three of these are T12s. This one up here is a high output. It's got a single pin. And this one is a very high output. It has a recessed double pin. So here we just have a diagram showing some of those different comparative diameters. Different fluorescent lamp types will then require different circuit connectors, and these circuit connectors are known as tombstones in the field. If you have a T5 or a T8 or a T12 lamp, they will require different sizes of tombstones, as well as if it is a bipin or a recessed bipin or a single pin. Each one requires a different type of tombstone, and so it is important to make special note of what type of fixture and lamp is in a particular luminaire if you're going to replace a few of the different items, because you don't want to go to the wholesaler and get the wrong thing. The other item that's required for electric discharge lighting is something called a ballast. A ballast has a purpose to create a very high voltage initially to establish an arc from one of those little filaments at either end of the tube to the other end. And once it has established an arc of current through it, then it will lower the voltage. And by lowering the voltage, it keeps the current down. And so it sort of has a two stage process. Starts very high, and then it drops low to ensure that the current value does not peak beyond what it's designed for. The ballast must be rated for the specific type of lamp utilized, and in this particular one, it looks like it's a T12 ballast. Some ballast are able to operate either a T8 or a T5, but most are specific to the type of lamp that you're utilizing. There's lots of other ratings. One of them I want you to be aware of here, open circuit voltage. This would be the voltage available at the tombstones if we had no lamps connected into the circuit and if it was energized. That's 1,000 volts. And so it's always important when you're relamping live lighting fixtures that you don't touch the end electrodes as you're inserting the tube, because one end of the tube could be inserted and the other end could be your finger across them, and 1,000 volts feels very tingly. So you don't want to have that happen. Voltage to ground, very high again. Power factor, sound rating. Sound rating, this one is a Class A, and that's because it's an electronic ballast. Class A is the best sound rating, which means it's the quietest. Quiet is good in areas where the sound could become an irritant. They're also a little more expensive. Class F would be the lowest or poorest sound rating, and that would be a very loud ballast, and you'd hear a humming noise, sort of like like that. This ballast, you'll notice, is not a high output or a very high output, and because of that, you'll notice here it says minimum starting temperature 10 degrees centigrade. So if you're in a location like a walk-in fridge or freezer at a large food storage warehouse, this lamp is not going to turn on with this ballast. You would need to get one that's specific for the application. Here are the two different types of ballast we have for fluorescent fixtures. The one on the left is called an electronic ballast, obviously, because it has all sorts of electronics in it. Newer, lighter, more efficient, multiple voltages, and it is able to establish a very high voltage to arc across the tube and then drop the voltage down to limit the current. On the right-hand side, we have the older magnetic ballast, older, heavier, less efficient, and it's filled with tar. And typically these things will fail over time. And when they do fail, you'll end up having some of this tar leak out from the actual metal enclosure and drip into the tray of the fixture itself. It's quite a messy, disgusting, gross sort of finding. And it's typically these do have PCBs in them as well, so you don't want to inhale dust from them or anything like that. Ballasts can sometimes be set up or wired from the manufacturer in one of two different ways. This ballast here has a wiring diagram fixed to it that shows that it is able to operate with either two lamps connected or a single lamp connected. And so this is easy for the manufacturer to produce one ballast, and then they can sell it in single or dual lamp fixtures. For troubleshooting, if this particular fixture had only one lamp in it that was dead, the other one would most likely continue to operate. And it kind of depends on the type of system that it's set up as. This one here is a dual lamp only ballast, so it can only handle two. And if you take one of the lamps out, the other one will de-energize as well. The other category we have of fluorescent is compact, and these have by far become less and less used, and that's because LED pricing has sort of pushed them out of the market. It has a ballast in it, and it's a linear tube that's been bent into a spiral. And they're very hard to dispose of in the residential market, which is really what these were predominantly aimed at because they had a Edison base to them. Before that, fluorescent was really only for commercial and institutional installations because very few people in a home had a linear fluorescent fixture. High intensity discharge. There's two different vapor areas to these electric discharge lights, an arc tube and a bulb. Current passes through and excites a vapor in the arc tube, same as a fluorescent fixture, but in this case, it simply produces more light and it burns hotter. Light is produced by this excited vapor and not necessarily a coating on the glass, although there are a few types that do. There is one type of light that sometimes gets grouped in here. It's called a low pressure sodium. It's the same operation as an HID, but it is lower in pressure, and we'll sort of look at that in a few moments. So why on earth would you want an HID light? Well, the reason for HID is that it will produce significantly more lumens for when compared against any of the other lighting options. But what about this one? How about a high intensity discharge versus a T8 or a T5 linear fixture? They're pretty close. And so what you can see here is that the amount of light per lamp, so one bulb puts out far more light than one T5 or one T8 bulb. And so just the number of components that you require is far less. This is what a typical HID looks like. It's got a shroud to reflect the light down as well as protect the bulb because it burns extremely hot. This up here is a enclosure that we take apart in two pieces, and inside is the ballast. It's got a hook here on this particular brand that supports the weight of the whole fixture, and then this flexible cord is the connection to the branch circuit. Inside a typical HID lamp, you have a rather large globe, and then inside that, the arc tube, and then you also have a bimetal shorting switch. So on a metal halide, you have a small resistor. It's right here, and that resistor is what's initially connected in series with the arc tube when you first turn the switch on. And what the resistor is doing is it is oh, actually, I've just screwed that up. The resistor is not connected in at the very beginning, and full voltage is put across the arc tube, which establishes the arc. And then once it heats up, there's this switch here that's a bimetallic shorting switch, and what that does is it bends as it gets hot. And when it bends, it puts the resistor in series with the tube, and what that does is limit the current. So it's a very basic system of limiting the voltage across the arc tube once the arc has been established. The problem with this is that if you were to turn the light off and then on again, as you've probably all seen in the field, it takes a long time for the light to fully illuminate again. And that's because this little switch here, heat activated, needs to cool so that the resistor is removed from the circuit so that once again, full voltage can be applied to the arc tube. So it's actually a really basic, almost rudimentary form of control that an electronic ballast on a fluorescent fixture would do automatically. Here are a few of the different types. We have mercury vapor HID, high pressure sodium HID, and metal halide HID. Mercury vapor and metal halide being probably the two most common in industry. All sorts of different sizes and shapes of fixtures, and the light bulbs being very large. One light bulb can be the size of a single phase meter base in some applications. We still have ballast for HID lighting, and typically it is a three-part or two-part component. It's a transformer, it is a capacitor, and then it may also have an igniter module, and then finally the connection to the lamp socket itself. This is a typical diagram that we would get on the side of the ballast to show us what connectors connect where. So over here is the voltage back to our source. We got a capacitor, there's an igniter module, and then here is the actual lamp itself. It is a screw shell type of lamp, so it's same as a typical incandescent, simply larger in diameter. And just like the fluorescent fixtures, electric discharge ballast can be designed to operate on different voltages, most common being 120, 240, 277, 347. Fluorescent fixtures would simply do this automatically. So this one says 120 to 277, as in you can connect any voltage from 120 to 277 to the two black and the white conductor, and this thing will simply sort it out, and it will determine how to adjust for the voltage you've given it. Whereas on high intensity discharge, what we get is multiple connections with wire tags on them, and you just choose the voltage that is appropriate for the source you have, and you cap the remaining wires and don't use them. What about LEDs? LEDs are a light emitting diode, which means a diode which only allows current to flow in one direction, and when it is conducting current through it, it gives off light. LED requires DC to operate, and so we use a driver, which is the name for a rectifier in the lighting world, to convert AC to DC. Some LEDs are dimmable, others are not, and it kind of depends on the application if you need it or if you don't need it. Here's an example of a LED with a driver, and you can see here the individual LEDs and the DC conductors to the driver, and then this would be AC out the other side. We can replace high-intensity discharge lights with LED, exterior lighting with LED. There's all sorts of different applications where LED may be used to replace an existing lighting source, and often it's because of the energy that's utilized. You can see here a comparison of a 600 watt metal halide fixture. You only need a 250 watt LED fixture to provide the same amount of lumens of light. So there are some advantages to going with LED. HID requires some replacement costs to be considered through the life of the installation, and that's because the ballasts fail over time, as do the light bulbs. And these fixtures are typically hung from a ceiling in a warehouse, which means you need a man lift in order to get to them. You can't just use a ladder. And so the cost of maintaining a large warehouse with hundreds of these starts to become rather extensive, and a consideration of possibly replacing them becomes more desirable as the maintenance costs increase. An easy way to do a calculation for it would be to simply determine the kilowatt hours of the existing lighting system, which would be looking at the amps of one of the lamps of the existing system, multiplying it by the total number of lamps, and then by the total number of hours that the installation is on per day, and then getting a cost of, or a kilowatt hours per year rating, and then multiplying that by the cost of PC Hydro, and that would tell us how much approximately the owner is spending on lighting alone. Warehouse systems are pretty easy to do for this because the lighting is on for a set period of time. It's more challenging to do in a residential application. Then you do the exact same calculation with the same number of hours for the new LED lighting system, and we do a dollars to operate per year of this new system. And then, of course, we have to calculate how much it costs to even, labor and material to put in all the LED. What we do then is we take the old cost and subtract the new operational cost, and this would give us a yearly savings with LED. And with that, we could then divide the total cost of this new proposed installation by the savings per year, and that'll give us a pretty rough estimate of the total years to pay off the cost of the installation. Now, this is a pretty rough ROI, or return on investment calculation, that you can do for lighting. So make sure that you check out Section 30 of the CEC, Rules 700 through to 712, that are related to electric discharge lighting.